Okay. Okay, here's what I did. I'm working on this bottom portion of the circuit, line 409, I guess. And I've got the two bulbs, and I've got this little switch that I made out of the copper wire. All right, so I got a switch. But what I've done is I have not cut under the green light. I've got a green light and a red light, and I didn't cut the circuit, which would have made the current flow through the bulb. It's still flowing underneath it, so that's not cut, but this one is. All right, now I want to explain something about voltage drops, because under normal circumstances, there's only one load per circuit. All right, that's very important. One load per circuit. All right, well, if this is the one load, this one should use all 12.8 volts. Okay, well, this bulb and this bulb are practically identical. They're at least the same part number, or one number off. So I'm assuming that the current flow through each of them is going to be roughly the same. But here, they're acting in series as a pair of series resistors. And if you remember, series resistors increase resistance. And, you know, we've talked about it, that volts and ohms make amps. And if we put two resistors in series, if you remember from the previous card, we add them up, which means the current flow should be less through both than through one. And we're going to do that here, and I'll show you, because what I'm going to do is I'm going to use the amp meter to turn the circuit on and read the current, write it down, and then we'll put the green bulb in it and read the current, and it should be roughly half. All right. In addition to that, the voltage drops will be half. So this one should be approximately 6.4, and this one should be approximately 6.4. There's two ways to think about that. Either this bulb will be robbing energy from this bulb, or more resistance means less current means the bulbs get less hot. Either way works, okay, but there is a difference. All right, so let me use the amp meter real quick. Turn this on, milliamps. Put my regular leads back in. It takes a little bit of time to do this. This is all part of the thing. I got to move the red lead, actually. Got to move the red lead. I got to move the red lead from here to here for milliamps. All right, so put that back where you can see it. And I will turn this light on, I hope. And in doing so, we should be able to write down the current flow, which is 61.9, or we'll say 62 milliamps. Okay, so we're dealing with 62 milliamps for one bulb. Okay, well, if we increase resistance by throwing another bulb in, that number goes down. Well, if that number goes down, then there's less current flow through each bulb, and the bulbs cannot get as hot or as bright. Or you could say that this bulb will be robbing energy from this bulb, and then if you look at Ohm's law, it's proportional. So if this is half and this is half of the resistance, then they each will drop half the voltage, okay? Because voltage drops have to add up. So whatever the voltage drop here is, plus the voltage drop here has to add up to pretty close to 12.8, okay? So 62 milliamps. I'll put my voltmeter back in here, and turn on volts, and we're reading 0 because it's the same on both sides. And when I turn the light on, I get my 12.8 volts. Okay, but let's see what happens when I cut here. And I turn it on. They're still both on, but they're on not very bright. And look what happened to my voltage drop across the red bulb. The red bulb should have been using 12, but it can't because this green bulb is using up half of the 12. And why is it using half? Because this resistance and this resistance are the same size. Okay? If we were to put different size resistors in, then we would get different values, all of which can be calculated with this one simple formula right here. You just have to know how to apply it. Now the question then is, did my amperage go from 62 milliamps to 31? So I'm predicting it's going to go from 62 to 31. And why is that? Because 31 is half of 62. The bulbs are half as bright. The resistances are the same. The resistance has doubled. And the ass backwards of 2 over 1 is 1 over 2. And since resistance and current are teeter-totters, my resistance went up, so my current came down. Okay, so what I can do here is turn this off, put this back to milliamps, take this out. This is a pain in the butt, admittedly, no question about it. But that's just the job. That's just how it works. Okay. And now if I read amperage, I am hoping and predicting that with this bulb and this bulb in the circuit, double resistance means half the amperage, and I'm looking for a number pretty close to 31. And we get 40. How can I explain that? I mean, the meter is what it is, right? And then if I jump across and turn this light out, it does go to 61. When I take it out and put it back in, it goes to 40. Okay. Well, the best I can tell you is that because the bulbs are not getting as hot, this is an interesting sort of experience. Because the bulbs are not getting as hot, then they're not having as much resistance, so the resistance is effectively less than it would be if they were both fully bright. So there's about that's actually 30%, I think. That's kind of interesting. That's an interesting phenomenon. I don't know that I ever really thought about that. I can kind of relate to it, but I'm not sure I thought about it. So there's both of them. That's 40. I was expecting 30. I didn't get it. Okay? And the meter doesn't lie to you. But I do know that both of those bulbs are effectively equal to each other. And that would explain the difference, I think. So that's how that works. And what I want to do is show you what happens if we change this from a normal switch, for example, to a corroded switch. And I'm going to do that by putting a resistor in. And when I put the resistor in, the resistor is going to be a switch, but it's also going to be a switch that has resistance or added resistance or corrosion. All right, and I'm going to fix this so that it doesn't work. I'm going to go back to the red bulb only. Okay, so now the green bulb is out of the picture, red bulb only. All right, now let's see how we find the bad switch. How do we know the switch is bad? Okay, well, I turn on the bulb, but you notice the bulb is not as bright as if the bulb was working normally because the switch wasn't broken. See? So the resistor here acting as the switch is also interrupting some of the current. And notice that the light is using up 8 of the 12 volts. So what does that mean? Well, it means that this bulb is only using up 8, which means if I do the math, because Kirchhoff's law says, okay, Kirchhoff's law, that's the voltage drop law. Kirchhoff says that this voltage drop plus this voltage drop must add up to the battery voltage. Must never forget this law. You can call it the voltage drop law, you can call it Kirchhoff's law, but you must never forget this law. So now what I'm looking for is about 4.6 volts across my corroded switch. And I get 4.57. So my prediction is pretty close. So I was getting 8.17 or 8.18. And 4, so 4 and 8 is 12, 57 and 10 is 67, and 8 would be 75, so I'm looking for 12.75 in total, and lo and behold, I get 12.75, okay? So 4.6 plus 8.18 equals 12.75. So the voltage drop across this resistor plus the voltage drop across this resistor adds up to equal the total voltage. Okay? And if you want to ask yourself mechanically why that's true, it's because this point right here is connected to the battery positive, and this point right here is connected to the battery negative. So if I keep following here and I keep following here, go all the way up, 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 guess where I'll end up? I'll end up at the battery. And what should I read across the battery? Battery voltage. I changed the resistor in the switch here from 100 ohms to 330. So if I turn this on, my bulb is on, but just barely. Let me get this where you can see it. You can see the bulb turning on, but it's really weak. Okay? So the bulb is on, all right, but it's just not doing a lot of work. These little switch doohickeys are not the easiest thing to use. Maybe one of you guys can maybe come up with a better one. Okay, well, let's see what we got. Okay, now the voltage drop across the bulb was 8. And now the voltage drop across the bulb is 3.5. So the first thing we do is subtract. So 12.75 minus 3.55 is 9.2. So this should be 9.2. And sure enough, it's 9.27. Totally predictable. It's all predictable. And I said this would be roughly 3/4 of the total. And this would be roughly 1/4. Well, that's not too terribly far off. And it's off, but it's not terribly far off. Because 3.5, if we multiply that times 3, would be 9, 10.5. And we're off by a volt. Okay? So, that's close to the prediction. It's not perfect. I'm not going to claim perfection, but it's close. Okay. Okay, so what does that mean? That means the resistor here is consuming 9.3 of the volts and getting hot, and it's robbing this bulb of the energy it needs to be bright. the way that you normally check components in the real world is you pull them out. So I was trying to pull the bulb out because it has these little notches here, but I didn't do it. So what I'm going to do is I'm going to unplug the bulb. And I'm going to unplug the bulb by desoldering it, which is a little tedious, but that's what I'm going to do. So now the bulb is out. I have an open circuit here. I have a closed switch. And this is why I invented this tool that finds corrosion in wiring, because now I can simply read where the bulb was and I get full system voltage even though this resistor is in the circuit. And why is that? Well, it's easy. This resistor does not have enough resistance to slow current down enough to make this meter not read. This meter requires so little amperage that it still gets enough with that. So what I did was I added this button. And when you load the circuit by pushing this button, watch what happens to my voltage drop in my meter. Or watch what happens to my meter. See it drop? Okay, that means I have a corroded circuit. So basic troubleshooting here, since we're reading voltage, this is kind of how I want to wrap it up. Because I see system voltage, I cannot have a short to ground, because if I had a short to ground, the fuse would blow and it would go to zeros. I cannot have an open, because an open would be a broken wire, and if I had a broken wire, I wouldn't be seeing 12.84 volts. Okay, here's the last thing I want to show you. I've got my voltmeter leads connected here and here. Okay, so what I'm doing is I'm reading the voltage on the positive side and the negative side of this open socket where the switch, where the bulb would have been connected. Okay, so I took the bulb out. The bulb is out, as you can see. The bulb is out, so I've technically unplugged the bulb. I'm on the back end of the truck. I'm on the back end of the coal mine. I'm in the coal truck. I'm at the AC clutch of the pickup. I'm at the headlight of the vehicle. It doesn't matter, because all circuits are the same: power, ground, load, and switch. And notice that I'm reading full system voltage. Well, what I want to do is I want to show you what happens to the reading if we do certain things. Okay, so the first thing we're going to do is we're going to create an open. And I'm going to create an open by simply cutting the wire here. And I want you to watch the meter. Okay? Watch the meter. When I cut the wire, look at the meter. The meter goes voltage. See that? It's no longer reading 12.8. If I complete the circuit, I get system voltage, but as soon as I break the circuit, the meter jumps to this goes voltage, and we start getting these funky readings. Okay? That means I have an open circuit. I built an open circuit right here. Okay? So I've created an open circuit right there. Okay? And see, even just the tiniest little bit of connection gives you full system voltage. So let me open that up a little bit. Okay, so there's that. So there's the open. And the open is causing the ghost voltage reading. Okay, and the meter's going to jump around, and you're going to get 9, 3, 2, 6, 4. You get all kinds of different readings, and you get all kinds of funky things. Okay, so different meters respond differently, but that's called ghost voltage, and that's a good thing. Okay, now the next thing I'm going to do is I'm going to fix the short, or fix the open, sorry. And when I fix it, it should go back to source voltage, which it does. But this time I'm going to make a short circuit. And the short circuit is going to go from his ground right here to after the switch, which I think it just did. It did. Damn it, Jim! I'm a doctor, not an electrician. Ow! Obviously not a very good solder either. Alright, let me clean this off. Let me... That's why I put fuses in. Let me put another fuse in. I didn't mean to do that then. I was a little ahead of myself. Alright. And we'll put another one here. Hey, boo-boo bear. Okay, so there's my obviously necessary fuse. And I got the switch turned off. Yeah, switch is off because I'm reading open circuit. I'm reading ghost voltage. Open circuit here, ghost voltage. So this confirms that the switch is off. So what I'm going to do is I'm going to put the short here. And then I'll show you how the meter shows you a short to ground. Okay, so here's the short. And the fuse should blow when I turn the circuit on. So here's the short. Can you see it? Right there. There's my short to ground. I've got the ground connected directly to the positive wire coming out of the switch. So that means if you pay attention to right here, then what should happen, okay, is that I'm going to read that 0 volts even with the fuse blown because pow. Okay, but why am I reading 0, 0, 0? I'm reading 0, 0, 0 because my positive wire, which should have voltage in it, doesn't have voltage anymore because the fuse blew. So it's not sensing 12 volts. My ground is touching ground because my ground touches ground and ground is 0. Well, this positive wire is also touching ground because of the short. So the short is connecting my positive wire to ground. So the red wire is touching ground, the black wire is touching ground. 0 minus 0 is 0. Okay? So that's how that works, and that's why it works. So the short is after the switch. And I know that because the fuse didn't blow until after the switch was closed. But now, interestingly, here's the switch, and the switch is now open. If I fix the short, the meter should go back to ghost voltage. And it does. This meter is a little screwy, but it does do that. So there's my ghost voltage. Okay? Then if I fix the fuse, somehow or another, and I turn the circuit on, I get full system voltage. So that's how you find a short. Okay? You read voltage, you just read voltage, and you read ghost or 0, full voltage, or a voltage drop. So I showed you the voltage drop with the resistor switch. I showed you the short to ground. I showed you the open. And all of those existed. And when they all existed, rather, they were all immediately identifiable on the meter. So if you see system voltage, the next thing you should say is, I don't have an open or short. And then when you say that, then you can load the circuit with this tool. And if you load the circuit with this tool, then you're checking for high resistance, which is the third fault. So if any of you guys work in the field, you guys might think I'm being a hack. But the bottom line is the tool works. It's got a CAP part number, Volvo part number, UPS part number. A lot of people are using it. And it works. And if you use this method of ghost, 0, and drop, then you're going to start fixing things a little quicker. So the problem is that the voltmeter without this tool, which is called the Load Pro, the voltmeter can lie to you. Because right now, the average person would say, well, I've got good voltage, I need a new light, or I need a new motor, or I need a new clutch, or I need a new whatever. But by going to the circuit, turning it on, and then simply loading the circuit with this button here, notice that I'm getting a drop in voltage. and that drop in voltage tells me that I have corrosion in the wire. So if any of you guys watching have or working in industry in anything that's exposed to the environment, this tool, which is called Load Pro, is less than 60 bucks roughly, give or take a little bit, and it works with any digital voltmeter, and it saves your butt because now you can find all three faults. Dose voltage gives you an open, 0 volts gives you a short, and if you read a drop in voltage, that means you have corrosion, and that's all there is to diagnostics. If you can do that, you can fix anything.